So thank you very much for inviting me today. I look forward to going through with you our plans and getting your feedback into what we're doing. So our mission is to make the discoveries that defeat cancer. We're part of the University of London. And the overview of my presentation today is given here. So I'm going to discuss the life cycle of data that we go round in our institute and then map it on to the infrastructure that we're building and explain how we will make this whole thing work. So it's in 5 parts. I'm going to talk about the ICR, the Institute of Cancer Research, and the Royal Marsden Hospital, the life cycle, the architecture, and then 2 challenges where I particularly seek your advice, and then to summarize. So starting with the Institute of Cancer Research, it's the top UK university for invention income. It's one of the top 4 global cancer research organizations, and it's recently been ranked the top UK academic institution in the recent ref review. So if you have an organization like this, how do you build an infrastructure that sustains this excellence? That's our challenge. And our income is interesting. We only have 15% of income from the government. So in order to fund our infrastructure, we have to actually take money from the grant income, from the researchers, not just to cover the capital costs, but to cover the full economic costs. So the services that we provide, we have to be able to recharge, and that adds a dimension of complexity and difficulty, actually. And we have 8 research divisions. You see the genetics and epidemiology division. Most of these do an NGS in some way. About 70% of the total computation in ICR is NGS related. But as we build our infrastructure, it's got to be flexible. It's not rigid, it's not sets of pipelines, it's people, PIs in each of these teams using our infrastructure to remain one of the best institutes in the world. So we have to be flexible. We can't build something which is very good at one thing but actually doesn't support other types of activity. The Royal Marsden Hospital is just next door. The principle is bench to bedside and back. And this means that the developments that we have in ICR are very quickly realized next door in the hospital. And we've been working together for more than 100 years. So this is our overall research strategy. We collect all the data for a patient that arrives next door in the Royal Marsden Hospital, genomic being key, but all aspects related to them. And then we put this into a knowledge hub where we collect data, the wisdom of the world, really, in order to then identify treatments. And these are then recommended for the individual patient at that particular time. And then the patient is treated. But as you treat the cancer, it evolves. And so you have to go around the loop over and over again as you continue to treat the cancer. And by 2022, we are planning to have individualized clinical trials in drug and drug radiotherapy. So that's our overall research strategy. Our infrastructure has to support this. And the London Cancer Hub is now being built, which is a much bigger enterprise. It's a world-leading science campus. And so we're growing and not standing still. So that's the background, and I've given you the background because it's actually very important to look at the background in order to design your life cycle for research data and how you implement your infrastructure. So now moving on to the research life cycle. The teams within those divisions in ICR are responsible for managing their own data around the life cycle. And it often starts with data creation coming in, perhaps a tumor sample from the hospital next door, and then data processing, data analysis going around many times, and then providing data access both within the institute and outside, and then it eventually gets to the point where the data has to be curated long-term. And in addition, we have the big data requirement to put it all together to give personalized healthcare. And as I said before, 70% of the computation in all this is NGS. We have some services within the Institute to mention a tumor processing unit, which I'll come to in a moment, and also a proteomics center. So there are some activities which are self-contained, but as the researchers overall are responsible for data around the whole life cycle. So I'd just like to take a poll here. How many here are in an institute which is trying to manage through this whole research life cycle? Could you put your hand up? So 10 or 20% probably. Of those, do you think you have most of the components in place to be able to do it? Anybody? One or about three? And of those, or any people put hands up, are you actually dealing with patient data? One, two, I think, two or three. Because the purple rings around these circles are patient data. And increasingly, we're having to face the challenge of dealing with patient data, patiently identifiable data. And that is adding another dimension to our challenge. So we have two particular challenges. I've just mentioned them here and then come back to them at the end. One is metadata management, how you move data from one part of the life cycle to another. And the other is how to deal with the patient data. So that's the life cycle. Now about the architecture. And the color coding is obvious, I think, that around the life cycle, the color then refers to the part in the infrastructure that we are dealing with that part. So I mentioned a patient comes into the Royal Marsden, tumor samples taken, goes into our instruments at the top left there. Yeah, here. And then we have staging areas that the data moves down to before it gets into our live data storage service here. Now, I think it's unusual in that we have a very fast, large live data storage. So we can actually go straight from HPC into this without bypassing Scratch altogether. And it's also so that we can do very fast image analysis, which doesn't relate to the HPC at all. So for example, cryo-EM, as in the last talk, we're going to have 300 terabytes of cryo-EM data before the end of the year. It needs very fast analysis, so it will come in through here directly in. The dotted boxes are parts of this overall infrastructure that we're building, and I'll go through these in due course, but this is to enable ingesting and exporting data very effectively. This is when the data actually is no longer actively being analyzed and it falls down into these repositories. And this data safe haven is how we're trying to deal with patient data, a new challenge and a difficult challenge. So that's the overall picture of our architecture that supports the life cycle. Now, I thought it might be useful just to look at one example, and this is the tumor processing unit. So we have a HiSec 2500 and Novosec 6000 in this particular unit. And the data is passed into that staging area that I mentioned. And then it goes, in this case, it does go into Scratch space. So we have 100 terabytes of dedicated space on Scratch. It has ring-fenced nodes on the high-performance computing, and the LIMS holds the information about the sample. And the analysis is done, and then when it's completed, it moves on to our research data storage service. So this is a typical exome analysis. The FastQ conversion happens first, and then there's the BWA indexing and aligning, and then call variants. And all the time, the data is becoming more compressed. But we actually store these FastQ files as well, so that you can go back and repeat it. So we store that as well as the outcomes of the analysis. So now let's go back to this overall architecture and focus in on this RDS storage service, and I can explain how it's developed. So recently, in fact last week, DDN published a case study on it. You can find it at that URL, and it's given here on the right. It consists of two tiers, a top tier which is a stretched cluster with GS7Ks with synchronized mirroring between the two, at 2 petabytes, and then 4 petabytes of object store using GOA. And the user who puts data into our store, irrespective of which of these tiers it's on, sees a single file directory. So the whole idea is that this is very easy to use. User puts the data in and really doesn't need to worry very much about it. It's very fast access. It's 2 gigabytes per second on the top tier and typically 0.4 from the object store tier. And we have it over 3 sites. So we have the storage in these 3 locations, and the researchers are in 2 locations here and here. And we deliberately chose this for the robustness, but we don't have backups. We just have the resilience provided by the 3 locations and the GOA for the objects and the replication for the spectrum scale at the top. Since the beginning of 2017, this shows the increase in storage. This is 1.6 petabytes now. It's slightly more than linear, I think. So key is that this overall service is accessible from lots of different places, even from your laptop, as well as from HPC. And we have a very well-defined policy for appropriate and secure use. We take snapshots daily, which are kept for 3 months. So if somebody deletes something by mistake, we can recover it for up to 3 months. And we charge the top tier at £300 a terabyte a year, and the object store tier £150 a terabyte a year. So what have we learnt after nearly a year and a half into this experience of running this service? I think it is an unusual use. We have the very fast access used by people doing completely different science for live data. We have to be flexible in everything we deliver. We did have difficulty with the small files. The small files have been mentioned several times today. We have hundreds of millions of small files on our service, and we found times to improve the access for these small files. Happy to explain if anybody wants to know about that later. We actually delivered this as a service that people put data into the top tier, and if they didn't touch it, it would then fall down to the lower tier automatically. This is what the researchers wanted when we built it. This wasn't what the researchers wanted once they used it, as often happens. They want to be able to move it down to the lower tier at their discretion, particularly because it's cheaper. And so we have changed it to do that. The message really is that delivering something like this, you don't just deliver it and that's it. You continue to evolve it. And the relationship with your provider, and DDN in our case, is very important. So we work together. When we get new challenges, we work together. We work together on the small files, access times. We work together on restructuring the overall architecture. And the third lesson is that recharging is very difficult. It's difficult when people have money coming into research grants to really get a fair way of extracting that. So let's take these services which are now under development, go through them very quickly. The external data sharing service, this is to import or export up to 10 terabyte research data with appropriate levels of security and assurance. And this will include clinical data, being able to move that in and out. And also to have a web-based software so that we can actually present our data outside ICR, where people can use database to search and decide what they wish to see. So we're starting with a NAS server, which then has data transfer nodes, and we're starting with something called Zen2, and then I think Globus is our next priority, and so on, to meet the needs of the researchers that wish to transfer data. The publishing repository, the idea here is that we can deposit, share, cite data both within ICR but also externally so that they will have DOIs. We're going to have a single catalog, so if the data is in a national repository or discipline-specific repository, it will be in the catalogue, and if there isn't a place to put it there, it will go into ours. The preservation repository is for the long-term depositing of data. Many of the funders require now you to keep it for 7 or 10 years or more. This is where the data will go. It's essentially internal to ICR, but it's a way of keeping long-term the data that we wish to keep. Many of the studies are generation-long studies. And then the data safe haven. So this is a service for our researchers for holding, accessing, manipulating sensitive patient data. We're going to build, as I have shown in this purple here, a separate infrastructure which is controlled and secure and which is flexible. Not everybody needs the same level of security, depending on the amount of data you use, the type of data you use. And this is something which is very relevant in GDPR in Europe at the moment. So we're going to build a service that researchers can then tailor to their own particular needs. It will certainly have controlled and restricted access to the data and also downloads of the data. Data will be encrypted at rest and in transit, and every transaction will be recorded and auditable. So those are our 4 parts of the infrastructure that we're developing. The 2 challenges I said I'd come back to. So we collect metadata from the LIMS and directly from the instruments. We may well use PRIDE, which is a proteomics metadata definition, to define it, but we need to be able to then supplement the metadata as the data moves around the life cycle. But also we would like to be able to control moving data from one part to another. Now, IRODS does this, and ICAT also does it, but we don't have the resources to implement these. These require a significant effort to implement. So if any of you have an idea of an alternative way of doing it, please see me over lunch, because I'd love to know. We're thinking about using Globus to do it. It might be able to do it, and there's also Media Flux. But this is a question which is unresolved for us. And the second question is how we build this data safe haven service. It's becoming more and more important with GDPR. We can't find anybody who will accredit our service that we're designing. We're going to create this service that people can then tailor to their own needs. We're not sure how to do it. We're not sure how also to connect it with the rest of the infrastructure, because we need to do that. So again, over lunch, be very pleased to hear any advice. So last slide, Jeffrey. So conclusions. In order to deliver our research strategy and dynamic adaptive therapy, we need to have this big data capability. We need to, therefore, to do that, manage data through the research lifecycle. And within this, we have to deal with patient-identifiable data. It's up to the researchers themselves to manage their data through the life cycle. And for that, the data controls and security for personal data will become more and more important. So we're establishing a combination of the services, the policies, and the support for our researchers to manage through the life cycle. At the core of everything is our leading RDS service. We're adding the external data sharing service and the publication and curation repositories, and also the data safe haven service. But we have 2 particular challenges. One is the metadata one, and how to move the data around the life cycle. And the other is how to build a versatile but secure data safe haven service. Thank you.
Questions? Paul, imagine you would all like to have a system like that.
Yes.
You're talking about the metadata that you're trying to manage. So what format do you keep your metadata? Is it floating around as spreadsheets?
Yeah. Most of the metadata at the moment is actually just by file name and file directory. That's all there is. But when we have the instruments, we have much more. So we can collect from the instruments at that point in the life cycle decent data, because the instruments will only work if the people give them the data. They won't do it. So we've got that strong point, but we haven't got a point to follow. But We don't even have a system at the moment, even if we could get. Thank you. Thank you.
So what are the architecture? The reason you put the scratch
Yes.
in the middle, and it's because you have to actually compute anything there.
So if we didn't have the scratch there, the RDS service would be overloaded and it would be dominated by its relationship with the HPC. So we need it there. But as a buffer, exactly. But the RDS is fast enough that some people just go directly to RDS and don't put it into scratch. We don't recommend it actually, but it works.